Okay, let's go ahead and get started. Today, we're going to discuss a concept that's very, very important to your everyday life. We're going to talk about magnetic induction, which is the way that we light up our cities. We don't have a big warehouse somewhere filled with batteries that we use to light up the city. We use this principle of magnetic induction that we'll discuss today. Someone in the mood to give us a morning prayer, get us started today? Good brother.
Our dear Father in heaven, we're so very grateful for the chance we have to receive an education and enjoy learning about science. We ask the Lord to help us to better understand the magnetic model as we learn about more about it today. We're grateful for thy Son, Jesus Christ, and the new life he gives us. Help us to remember that he lives, and that because he lives, that we can live again, and that we can enjoy this mortal life more fully. And we say these things in the name of Jesus Christ. Amen.
Okay. Before we talk about the new topic, let's do a quick review. I have this loop of current going in at the top and out at the bottom, down in the back. You remember the donut model, and it's fixed in place. We glued it to the sky, okay? And we've got this bar magnet that's free to rotate about that orange dot there. And the question is, will it rotate clockwise or counterclockwise? So with your clicker, get your clicker out, please.
Everybody at every lab.
This one is it goes into and then sample's not going to go. That's where the north is. Because this is like they're like we're on two. Magnus didn't align itself with so I like that's
okay. Last call. Okay, counterclockwise is the correct answer. Let's go through the reasoning real quick. First of all, that little bar magnet is responding to the magnetic field of the loop. And so if we use our right-hand rule to figure out, essentially to replace that loop with a bar magnet, okay? So our fingers go in at the top, out at the bottom, and my thumb is reminding me which direction is the north side of that, that loop. And you remember, field lines come out of the north, wrap around and go into the south. Well, I don't care what that magnetic field's doing over here. It's over here where it's affecting the bar magnet. And over here, it's towards the south side of that loop. Now, again, that bar magnet, because it's free to rotate, it's a compass needle. And so it's going to line up the north side of that bar magnet is the arrowhead on the compass needle. And it's going to line up with the external field that it finds itself in. Check on your neighbor. Do a buddy check. That's very similar to the homework.
So this is the tear. That's the way yeah.
Okay. We ran out of time last day before we could talk about the electric motor. And it turns out that electric motor is can be a very simple device. There are many designs for electric motors. Some of those are very complicated. But I've been able to make an electric motor just with a bunch of wire that I've wrapped in a circle, and then I've mounted that on a couple of stands and brought a couple of magnets nearby. I get that thing really humming there. It's not that complicated. And so the principle, the idea is that if I have current going in a loop, that looks like a bar magnet. And if that loop is free to rotate, that looks like a compass needle. And if I can put that loop in some external magnetic field, those are the blue lines there, those could be caused by a horseshoe magnet or a couple of bar magnets or electromagnet, doesn't matter. However I set up that magnetic field, that little compass needle is going to want to line up. And if that were the end of it, I mean, if it just lined up, that wouldn't be a very impressive motor. You wouldn't pay money for that, okay? So the secret, the big secret, is right at the moment where the compass needle lines up. Watch carefully. Did you see that? I want to switch the current. You see the current's coming out towards you at the top? I want to go pow, okay? And that's going to change the direction of the compass needle so that now it's not lined up. And then it will line up. And as soon as it lines up, pow, I switch it again. And then it lines up. I just keep on switching it at just the right time. And that's the secret to a motor, is switching that current at just the right time. How do we do that? Well, we do that in this way here. What we've got, we call them bushings, okay? Sometimes they're called commutators. Filthy commutators, okay? Anyway, you see that these bushings are pushed up against these leads. And so right now, this lead right here is connected to the negative terminal of the battery. But a half turn later, this lead's going to be over here connected to the positive terminal of the battery. And that's going to switch the direction of the current in that loop. Right now, it's going clockwise, but when it goes half a turn over, it'll be going counterclockwise. Now, I've got an example here. This is a simple motor. Those of you in the back are going to have a hard time getting all the nuance here. Here we've just got a horseshoe magnet, north side here and a south side there, giving me that magnetic field that we saw, the blue lines. And then I've got this coil that's free to rotate between that North Pole and the South Pole. Now, the really important part of this is these bushings. Okay, let me see if we can make everyone see the bushings. I've got these, they're just kind of pushed up against this collar, but this collar is not really a full collar. it's two half collars. You see, it's got a slice here and it's got a slice on the other side. It's two half collars put together. And so, when I turn this up, right now, this collar is hooked to that bushing. A half turn later, it's going to be hooked to this bushing here. See how it switches every half turn? So let's make this work. By I think I can make it go faster. Can't hold it much longer, Captain. Okay. And that's the idea behind a motor. See if your neighbor could make a motor later this afternoon.
I don't know what happened. It's part of the, but like. Stand, but
Now, in principle, that electric motor is just operating on the idea that we discussed last time of the jumping wire. That if I've got current going through a wire, a magnetic field is going to exert a force on that, and that's what's causing this thing to go round and round and round. But today we're going to revisit that jumping wire and look at it a different way. You remember what we did before is we had a horseshoe magnet with a north side here and a south side there. That means the magnetic field was going out of the north and into the south or to your right. And what we did is we put a wire in there and hooked it to a battery. And we hooked it to a battery such that conventional current was coming towards you. And that flow towards you was in a magnetic field towards that open door. And if I use right-hand rule number 1, the flow is this way, the B field is that way, I got a force that was up and it jumped. And that allowed us to make a stereo speaker, okay? Now, what I'm going to do this time, however, is I'm going to get rid of the battery. You see the battery's clear over there. And this time I'm just going to take that wire and I'm going to shove it down between the poles of the horseshoe magnet. Now, it's important, folks. Today, it's really important that we use our imagination, okay? That we use a cartoon model of a wire. And that cartoon model is that this wire we can think of as a plastic tube filled with positive charge carriers that are free to flow through the tube, okay? And so when I take this wire and thrust it down between these, the poles of this horseshoe magnet, I'm taking all of those positive charge carriers and giving them a velocity down towards the table. You see that? As I push this down, that's bringing all the charge carriers down. They're moving down in a magnetic field that's again pointing towards that open door. What direction is my thumb pointing? Towards you. And it just so happens that that's the direction that the wire goes. And so if we're pushing those positive charge carriers towards you and the wire goes towards you, I create a current. They flow through the plastic tube, right? Now, I think I can help you see that. I wish that I had a more sensitive galvanometer. This is the only one I could find in the demo room. And it goes from a a milliamp one way to the milliamp, but another way. Now, watch what happens when I push this down. Did you see it? Did you see it? Okay.
Oh.
I can generate a current. Okay. And it's that current that lights up our cities. Okay. On Gilligan's Island, this is what Gilligan did all day long. Okay. So that the professor had electricity. You don't even know what I'm talking about. It was a 3-hour cruise. You're so young. You're so young. I need to retire. Can't talk to you. Okay. So we remove the battery and we push that wire down. And because of that velocity and that magnetic field, I get a current. We call it an induced current. Induced because I can't see the battery that's causing it. It's magical. It's magical. And it's that induced current that lights up our cities. Now, it turns out that the first person to teach us about this was Michael Faraday. And Michael Faraday's biographers have described him as a man almost entirely innocent. Ladies, I would ask you, does that look like a man almost entirely innocent? No. Okay, yeah. Stay away from that type. Okay. Let me finish the quote. He was a man almost entirely innocent of the principles of mathematics. Meaning he couldn't do math. You can't do math, okay? But he gave us some of the most powerful physics of our generation, of our time. And so we're going to talk about Michael Faraday's contribution today. And I'm going to start with a little experiment that many of you have done when you were younger. How many of you have made an electromagnet when you were growing up? Some of you, okay. The rest of you probably have missed something in your childhood. Maybe you need to go revisit that, okay? You know, I remember Lillian McDermott, who wrote the tutorials, sponsored the tutorials. She was giving a guest lecture to a bunch of students at University of Washington, and she was talking about where the wires go inside a light bulb, and none of the students knew. And she came back to her office, did these people just not break light bulbs to find out how they work? Probably not. Probably not. Okay, so do that. So to make an electromagnet, what you do is you take some piece of iron like a nail and you wrap wire round and round and round and round and round. And then you hook that wire to a battery to get a current going around and round and round and round and round. And you see here that that's just not a magnet. But if I put current through this by closing this switch, now it's an electromagnet. Okay. And then if I turn off the current, it goes back to being not an electromagnet. Okay, I'm going to need those later to get in my office there. Now, Michael Faraday taught us that we don't need the battery. We don't need no stinking battery. What he taught us was that if we were to bring a permanent magnet near a coil of wire, let me hook this up real quick to the ammeter.
Easy.
You can go in. Oh, that's interesting. Why don't you want to go in? There we go. Okay. If I bring this permanent magnet near this coil of wire, is it moving? Oh, good. I'm struggling here because I know that it's better for you if I'm back here so that you can see the ammeter, but I want to see the ammeter, and so I tend to do the experiment like this, and then you can't see what's going on. So I'll just assume that physics is working. Now, I want you to notice something. I bring this powerful magnet in and I park it. What's the reading on the 0? Okay, so it's not the presence of the magnet, but it's the change. Okay, when the magnet's coming near or when it's going away, I get that induced, can't see the battery that's causing it, it's magical current. Okay, when it's coming in or when it's going out. Now, to understand that, that current, let's look at it from the idea of right-hand rule number 1, okay? And I want you to, first of all, accept the fact that whether I bring the south pole near that coil or whether I bring the coil near the south pole, that's the same thing, right? That's not going to be any different, okay? Now, I need a volunteer over here. Who's willing to help me out? Jackie, are you willing? Thomas is willing, but he's always helping out. Okay. Jackie, this is the south pole, that yellow one there. And if you could just hold it towards me. We're going to consider this hula hoop that I borrowed from someone in my ward last night. We're going to consider that as a loop of wire. And we're going to play the same make-believe that we did with that wire over there. Namely that this is a, we're going to pretend that's a plastic tube. Oh, look, it is. And it's filled with positive charge carriers. Now, if I'm pushing the tube towards Jackie, all of these charge carriers are moving towards Jackie in a magnetic field that's pointing what direction? Yeah, towards that south pole. And so the velocity is to your right, but the magnetic field is pointing towards that south pole. And so now we're going to use right-hand rule number 1 to figure out the force on those positive charge carriers. Let's first of all look at a charge that's right here at the top. It has a velocity towards Jackie in a magnetic field towards the south pole. Now my thumb is pointing away from you, and that's the direction of the motion, away from you. If I look at a positive charge down at the bottom, it's moving towards Jackie in a magnetic field towards the south pole, and now my thumb's pointing towards you, okay? Now I can do that all the way around. If I look here, it's towards Jackie, towards the south pole, up, towards Jackie, towards the south pole, down. All the way around, it's being pushed in a direction counterclockwise as I view it, clockwise as Jackie's viewing it. Okay, let's give her a hand, please. Thank you, Jackie. Now, Faraday was trying to understand this induced current and asked the question, does there have to be motion? Does there have to be motion? Well, clearly, if I'm going to use right-hand rule number 1, the first step is to reach in the direction of the motion. But Faraday found that you could make this induced current show up without any motion. Let me illustrate that. If I take another coil here, And I put it next to the original one. And just to be in keeping with standard nomenclature, I'm going to call this new one, I'm going to call the primary coil. And the other one I'm going to call the secondary coil. And so let's see, I'm going to have this here. And okay, now we got it. Okay. Now, when I close this switch, I'm going to connect the battery to this primary coil. And I want you to look and see what happens in the secondary coil. The secondary coil is not hooked to the battery, it's just hooked to the ammeter, okay? And when I close the switch, did you see a current? Oh, that's why. My bad. Okay. Now what about? Yeah, more better. Okay. Now, did that current go away? Yeah, until I release the switch and it comes back momentarily. Okay. So what we see is that when I close the switch, I get a current in that primary coil, and for just a split second, I get an induced current in the secondary coil that quickly goes away. And I can leave this switch, I can leave that closed all afternoon, and I'm going to get nothing over here. Nothing. Until I open that switch, and then I'm going to get induced current the other way, the opposite of what I got when I closed the switch. Okay? Now, I don't need relative motion. So what is it that's causing this induced current? And at that point, Faraday thought, well, I'm changing the strength of the magnetic field in this coil. In my first experiment, I changed the strength of the magnetic field by bringing this bar magnet near. In the second experiment, I changed the strength of the magnetic field in this coil by putting current in the primary coil and turning this into an electromagnet. Suddenly a magnetic field appears where there wasn't one before. And that seemed to be the answer until he came up with a thought experiment that is one of the most famous thought experiments in physics. And it's this one here. Imagine, if you will, that you have some copper rails and you're looking down at this experiment from above like a seagull looking for a target, okay? Try to visualize that. Now, these copper rails are attached to the terminals of a light bulb, okay? The side and the bottom. Now, riding on these copper rails is a copper bar. Good conductor, good conductor. And somehow we create a magnetic field between the copper rails. That's what these little X's are. That's telling you you're looking from above, and so these magnetic field lines are headed towards the floor, away from you, okay? And that magnetic field is uniform. Tell your neighbor what that means. What does that mean? The magnetic field is uniform.
Any bits apart. It's the same strength here.
Making the current go up.
Practice. Right, we nailed this. Congrats.
Stand up, last slide.
Oh.
Okay. I hope what you told your neighbor was the spacing between these field lines is everywhere the same. And so that means whatever magnetic field strength I have here, I have the same magnetic field strength over here. If it's 1 Tesla here, it's 1 Tesla there. Okay, that's what we mean by uniform. Now, in this thought experiment that Faraday came up with, he said, why don't you push that copper bar to the right? Now, again, I can think of that copper bar, it's like a copper wire. I can think of that in the cartoon sense, where it's a plastic tube with positive charge carriers. And by moving the bar to the right, I'm moving all those charge carriers to the right. Well, let's use right-hand rule number 1. If those charge carriers are moving to the right in a magnetic field that's away from you, then that gives me a push on those positive charge carriers up in this picture. Well, that's a direction where they're free to move along the copper. And I'm going to induce a current. Now, we learned in the previous part of the class that I can't have a current here without having the same current everywhere in that circuit. What goes around comes around. And so that's going to light that bulb. That's going to light that bulb with induced current. Can't see the battery that's causing it. Okay? Now, why is this interesting? Why is this important? Because in this experiment, we did not change the strength of the magnetic field. It's exactly the same as it was before we started pushing the bar. And then Faraday made the connection. He couldn't do math, but what he could do was visualize magnetic field lines. They were real to him. He looked at this bar magnet and he could see magnetic field lines coming out of the north and spreading out, okay, and coming into the south and getting closer as they got close to the South Pole. He could visualize that. And so what he decided from this experiment, this thought experiment, was I changed the number of field lines that went through the loop. When the bar was here, I only had 15 field lines going through that loop. But when I got over here, I had almost 30 field lines going through that loop. I changed the number of field lines through the loop. And then he went back to these other experiments and he thought about it in terms of magnetic field lines. When the battery's not connected to the primary, there's nothing going on here. There's no magnetic field lines. By closing this switch, I turn this into an electromagnet. I change the number of field lines through this coil. That induced the current. In the first experiment, when I bring this permanent magnet, remember, Faraday could see the field lines spread out. And so he knew that when the bar magnet was over here, those field lines that spread out, they're not making it. Most of them aren't making it through that loop. But as I get closer to the loop, more of those field lines are going through the loop. I'm changing the number of field lines through the loop. See if your neighbor can visualize those field lines. See if they can use their imagination.
The bar that's used that I missed the last lecture because I was singing devotional.
Okay, yeah, control.
Just good.
Okay.
So like I walked like I don't.
I see one where he heard was the grading.
It was like a lot of. It's just like the tutorials on the bar.
In order
Yeah, it's like
in order to make this just as scary as possible, we give this a name, magnetic flux, and a scary Greek symbol. Okay? And that magnetic flux is really just the number of field lines. Okay? And we find that an induced EMF, what does EMF stand for? Battery. Okay? Battery voltage. An induced battery is caused by a change in the number of field lines through a loop. And that change in the number of field lines, we call the magnetic flux. How many field lines are going through the loop? That's how much flux there is. If I double the number of field lines, I'm doubling the flux through that loop. Okay? Now, the formula, it turns out, for that flux is just the strength of the magnetic field times the area. Now, you remember in the experiment with the copper bar on the rails, we were changing the area of the loop and hence the number of field lines. In these other experiments, we were changing the strength of the magnetic field, the B. Either way, we're changing the number of field lines. Now, I don't want to derive this equation for you, but I would like to motivate it. You remember that we represent the strength of the magnetic field, and we use B for magnetic field to honor Biot Savart, okay, a dead physicist. That is proportional to the number of field lines per cross-sectional area. Remember, that's the same way we used electric field lines, and we're playing the same game with magnetic field lines. The closer those field lines are together, the stinkier it is, the stronger the magnetic field that we have. Now, if I multiply both sides by the area, I can get this area out of the basement there, and what we see is that the number of field lines, that's the flux, is proportional to the B field strength times the area. And we can show that that constant of proportionality, if we use the right units, is 1. Questions on that? Okay. Now, we're almost there. We're almost there. I need to add a few little wrinkles here. What I have here is a flash bulb, and again, you're so young. This is the way we used to take flash pictures. We'd put this little bulb that's filled with magnesium filings. It would sit on top of our camera. And when we push the button to take a picture, we would connect a battery to this bulb, and that would cause a current to go through the bulb and ignite the magnesium to make a very bright flash. And that would light up the room so that you could take a picture of something in the back of the room. But it's a one shot. Once you put the current through that bulb and it exploded, it was over. Okay. Now, we don't use these bulbs anymore, but I'm going to use it to demonstrate a principle, and I'm going to need, what do I need? Well, oh, yes, doggone it. I need this. Oh! Let me put this further away from you people. Okay. Yeah. The BYU lawyers would prefer that I do this back here. Okay. Now, if I hook this to a battery, it's going to flash. But Faraday taught us we don't need no stinking battery. So instead, what I'm going to do is I'm just going to hook the side of this terminal to one lead of this coil. And I'm going to hook the other lead of that coil to this copper plate that I'm going to hold the bottom of that little flash bulb on. Okay. And then I'm going to change the number of field lines through this loop by passing it through the poles of this horseshoe magnet. Now, to make this as fun as possible, we're going to turn down the lights. Turn down the lights. Okay. And what lack I yet? Okay. So I'm going to put this on the copper plate and I'm going to pass this through the poles. What did you see? Nothing, because I lied to you, okay? I told you that what was important was how much we changed the magnetic field lines, the flux through the loop. The truth is, it's how quickly you change those field lines. You want to see that again?
Yes.
Just close your eyes. You're going to see it the rest of the day. See that the rest of the day. Okay. Now,
See you right there.
okay. Now, that was not dangerous. We tested that with grad students to make sure that it wouldn't hurt anyone. So you're fine. Okay. So what we're missing here is this idea here. This idea here. That induced flux, I'm sorry, that change in flux induces a battery, an EMF we call it. And that's the invisible battery that drives the induced current. And you see that it depends not only on how much we change the flux, the number of field lines, but how quickly. I've taught you many, many times that whenever you have a ratio, something divided by something else, you get a gut feeling understanding by setting the basement equal to 1. In this case, 1 second. So this is how much you change the field lines in 1 unit of time, in 1 second. How quickly you change the number of field lines. Now, there's something missing in this equation. We call this Faraday's law, but it's not quite right yet. There's a minus sign here that is one of the most famous minus signs in all of science. It even has its own name. It's called Lenz's law. And that's going to be the topic of this last tutorial, tutorial 10. And it's also going to be the topic of Tuesday's lecture next week. And this lecture Tuesday is my favorite lecture in 106. We're going to have a lot of fun. I'm going to bring in that $7,000 quantum levitation track that you can play with. I'm going to be floating stuff. It's going to be a hoot. Okay. Don't miss Tuesday. Okay. Don't miss Tuesday. We're going to talk about Lenz's law. Okay. There's one more piece of information that we need, and that is if I bring this bar magnet near this coil that has 500 turns, I get a pretty dramatic current. If instead I use this weaker coil that only has 200 turns, what I find is that I don't get as much of a current, okay? It turns out that the more turns I have in my coil, the more I change my magnetic flux through the coil. And that's because if I go from 0 field lines to 5 field lines through this circle, I have to count those 5 field lines for every single loop of the wire. And so 500 terms, I'm multiplying the 5 by 500. 200 terms, I'm multiplying it by 200. Now, what that means is that we have to modify our definition of magnetic flux. What we find is that magnetic flux is really equal to National Basketball Association. Okay, can you remember that? NBA. Okay, we have to multiply the B field strength times the area for one loop, and then we have to multiply that by the number of loops. Okay? Now, let's practice these ideas. Suppose, just suppose, you were put in charge of guarding the border, okay, keeping it safe, okay? And you know what border I'm talking about, right? That border with Canada. You know, our arch enemies that we've been at war with forever, okay? Those Canadians. And what you want to do is you want to protect our country from those Canadians that are trying to sneak into our country with magnets. Wily. So what you could do is you could take a door frame that you got at Lowe's and you could wrap wire around that door frame. And then you would force those Canadians to go through that door while that loop is connected to an ammeter. And if those Canadians tried to come in with a magnet, pow, you've got them, okay? Now, that's pretty easy. What's more difficult is guarding that border the other way, keeping the Americans from bringing guns and knives. We're a violent people into Canada, okay? And there, what you want to do is you want to be able to detect not magnets, but metal. You need a metal detector, okay? And you see that if let's let this represent a gun. It's not. I assure you it's not, okay? Oh, why didn't you tell me? This wasn't getting any kind of a response there. Wasn't connected. Oh, just let the old man do it. Okay. So you see that when I bring this gun through that magnet detector, I don't get anything. Okay. So what I need to do is I need to magnetize this gun. Now, one way to do that is to put a greeter at the border, and that greeter would say, "Excuse me, sir and or madam, could I please see your gun?" And then you could attach a permanent magnet to the gun, and when it went through the magnet detector, you'd have them. But that's only going to catch the really, really dumb criminals, okay? So a better approach would be to take a second coil around that door frame and to hook that second coil, actually what we call the primary coil, to a battery. And then when the gun goes through this primary with the battery connected, it gets magnetized. And then the magnetized gun gives me a reading on the magnet detector. Okay, see if your neighbor understood what we just did to make a metal detector.
That is magnetized by the electrical. When you say it, I saw magnetized.
Just understand it, just.
I mean, if
Okay,
I have technology where
That's why.
I have to like this primitive.
can anyone think of a way that you could still sneak this gun past the detector, Thomas?
Walk through it slowly.
Oh, yeah. If I walk through the door frame really slow,
Then they're gonna come back.
it's the old ladies that are packing. You're gonna have to put a bouncer at that door to throw those people through the door frame to catch them. Okay, now, people, before you go down to the airport and try to sneak something past them on TSA, let me assure you that my simple device here is a DC direct current device. Theirs is much more sophisticated and works on alternating current. And if you try to sneak something by going slowly, you are going to get a free colonoscopy, okay? You do not want to do that. Okay? You do not want to do that. Okay. This problem is almost identical to one of your homework problems. A wire is looped 10 times around a square insulator, something like plastic, is just holding the wire. And that insulator is 2 centimeters on a side. If we start up a magnetic field into the page in the diagram, so that it increases at a rate of 10 to the minus 5, a tenth of a Gauss, 10 to the minus 5 Tesla per second, what EMF, what battery voltage will be induced between the ends of the wire loop, between these two leads right here? If I were to measure the voltage between that lead on the left and that lead on the right, what voltage would I measure? Okay, so let's solve that problem. Well, first of all, we know that we only care about the magnitude of that EMF, of that voltage. We're going to talk about the direction on Tuesday. That's Lenz's law. So we don't have to worry about the minus sign till Tuesday. We just want the absolute value of that voltage. And that means we have to find how much the flux is changing, the number of field lines, each second that goes by. Well, you remember, flux is just National Basketball Association. So if we're looking at the change in that flux, well, the number is not changing. The number of loops is going to be 10 throughout the problem. And the area of that loop is not changing. That's just going to be 2 centimeters times 2 centimeters. But we've got to convert that to meters squared. Okay? So if I want to find that EMF, I just take the N and I take the A and I divide the delta B by the delta T, and that gives me that number right there. That's the rate of change, the change in flux, the change in magnetic field strength each second that goes by. And so that 1 times 10 to the minus 5 goes right in there. So there's my 10 turns. There's my change in field strength each second. And this is the, I converted the 2 centimeters into meters. It's 0.02 meters. And I have to square that to get the area. See if your neighbor could work that problem. If you're, because you're going to have to. It's the same as your homework.
That's sitting in front of me.
But then on Tuesday, it's gonna be like spot it now. I got it.
It's up to the lecture, so.
Like, I don't get it by. I'm sure.
Are there questions so far?
Yeah.
Okay. Let's talk about free lunch.
Fine.
Let's go back to this thought experiment of Faraday's, and let's imagine that these copper rails go on forever. It's a thought experiment. We're free to think big, right? And that everywhere between the rails, we have this uniform magnetic field. And again, we're looking down from above, like a seagull, okay? Now, let's suppose that these copper rails, since we're using our imagination, let's suppose they're frictionless. Why not? Okay? Now, we know from Physics 105 that if we get this bar moving on a frictionless set of rails, we don't have to keep pushing. What's moving wants to keep moving. That's Newton's first law. And that suggests that I don't really have to push this to the right. I just have to get it started to the right. And then it's just gonna keep on going at constant velocity forever and ever and ever. And because it's moving in that magnetic field, I'm going to get this induced current that's gonna light up that bulb, and I just got free energy. I just can light up that bulb forever as long as that bar is just sliding along the frictionless rails. Now, I hope your gut is saying, that can't be. I gotta pay for that light. Okay? So what's the catch? What are we forgetting? What are we leaving out?
The force required to move the bar.
I'm sorry?
You have to have something that's gonna move the bar.
Oh, well, once I get it started, Newton's first law says it just wants to keep going.
You need voltage?
I'm sorry?
Do you need voltage?
Voltage is what we're generating by changing the number of field lines. That's what Faraday's law gives us, is the EMF that is the voltage driving the current. What's missing is the right-hand rule again. When I was pushing the bar in the beginning, I was giving all those positive charge carriers this velocity here. But that caused the EMF that generated the current that caused this velocity. A current is the motion of charge. We think of conventional current as the motion of positive charge. And suddenly I've got that positive charge moving that way in a magnetic field that way. And that's going to give me another magnetic force that's fighting this motion. And that means if I don't keep pushing it, it's just going to slow down and stop. Okay? I have to pay for that EMF. I have to pay to light up that bulb by constantly pushing to fight that magnetic force that suddenly appears. Check that your neighbor understood what just happened there.
Whereas we're
Initially, we were looking at. Wait, you know, it's dust. So we're saying and that one. Oh, no, but I know that. What do you say? Like, oh, force a whole.
Okay,
But I think the second.
now, this is a general principle. That induced current has to be paid for by something doing positive there, something providing the energy to cause that current to go around. Now, we don't generate our electricity in this city by having copper rails in a magnetic field, but the way we do it is not that much different. What we do is we have a magnetic field, that's the blue lines, and we take a coil of wire and we turn it in that magnetic field. Now, that's changing the number of field lines through that loop. Now, think of this, let's use an analogy. Think of this as a butterfly net, okay? And there's butterflies in this room, okay? And if you're going like this with the net, you're catching butterflies. If you're going like this with the net, you're just making them mad. You're just smacking them, okay? You're not catching any. And so if we think of those blue lines, those field lines as butterflies, I'm catching butterflies, I'm not. I'm catching butterflies, I'm not. I'm catching butterflies, I'm not. I'm constantly changing the number of field lines through that loop. And that, we found, is going to generate this induced current in the loop that we can then use to light up our cities. Now, I've got a little generator here. And really it's just an electric drill from Home Depot, okay? And we're just going to use it as a generator. It's got coils in there. in a magnetic field. And so I need someone strong. I need someone on the football team. Who did you volunteer?
Wake up. It's true.
You were what?
Oh, no.
Come on down. Thank you for volunteering. We appreciate you. Thank you for your service. Okay. Just bleep it. Bleep it. What's your name?
Hayden.
Hayden?
Yeah.
Hayden, I want you to crank us some electricity there. Okay. Now, right now, Hayden is just, he is just fighting friction is all. Now, I'm going to turn on 2 of these lights. Did that get harder? Okay. I'm going to turn on 2 more in parallel. Harder still. 2 more. Keep them bright. 2 more. 2 more. Very hard. Okay. Let's give them a hand, folks. As Hayden was turning that loop of current in the magnetic field, we induce a current. And that current is always going to be in the direction to fight the motion. Okay? Now we know that whenever we have a current loop, we can replace that with a bar magnet. And in this case, that bar magnet is going to be in a direction where Hayden's always trying to move it the way it doesn't want to go. That bar magnet wants to line up with the magnetic field. It's like a compass needle. But Hayden was forcing it to go the other way. Okay? And once he got it the other way, if he kept going around, well, now it's going the way it wants to go. That never happens. It always fights. And so watch what's going to happen when it gets to this point. It's the current's going away from you at the top. Watch what happens. Pow! And then it switches directions. So that now, again, Hayden is fighting against the stream, against the way it wants to go. And then it gets to this point and pow! It changes direction again. And we have to always fight, always fight. Now, here's the thing. The more current that's going around that coil, the stronger the bar magnet is. And the more it's going to fight that motion. Now, we don't have someone like Hayden lighting up our city. What we do is we have these coils of wire hooked to turbines at the bottom of the hydroelectric dam. And that water falling off of the hydroelectric dam a great distance causes those turbines to turn in a magnetic field. And that's what lights up our cities. Now think about the city of Los Angeles on a very hot August day. Everyone turns on their air conditioner. And all those air conditioners are hooked up in parallel. Now we just learned in the last section that what does that do to the resistance of the city of Los Angeles? It decreases it. And that means it's demanding a whole bunch of current from the power supply, from the generator. Okay? And that means a whole lot of current's going to be going through those coils at the bottom of the dam. Now, when you get enough current going through those coils that the falling water can't turn the turbines anymore, then you have a blackout and nobody's air conditioner works. Okay? See if your neighbor just understood what I was talking about.
Like, you are the principles, like.
I just made this one a jumpsuit.
To say principle 2, is ask what you said.
Yeah.
That's what you can. On the flag. Don't mind. Yeah, that's all.
My friends.
Okay, got a clicker question for you. I have an electric fan. Is that electric fan, is that a motor generator, both, neither, or I don't know? Oh, haha, sorry.
Live.
Technical difficulties.
Just like a.
Not generating.
I don't know. Electricity. Sensor. You know.
I get it. All right, Braden, I think you need a competition.
Okay, last call. Get your vote in.
Yeah.
Okay, the correct answer is C, both. Okay,
Thank you.
now. It's clearly a motor because the motor is what's causing the fan to turn. Okay, and the current that's causing that turning is, well, that's from the power source, modulated by the commutators, the bushings, to be just the right time that they switch. But anytime I have a coil turning in a magnetic field, I also get this generator effect. And so there's really two currents that we can think about in the coil of this fan. There's the battery current that is driving the motion, that's making it go around. But then there's also this induced current that is fighting the motion, always making us pay for what we get. And one of them's going one direction to cause the motion, and one of it's pushing the other direction to fight the motion. We call that the back EMF, and we'll talk more about that on Tuesday. Now, this is, you know, a little bit too much to bite in the last 5 minutes of class. So why don't we just start our weekend early here and move on. Happy Easter, folks. Happy Easter.
I'm gonna watch some videos on that.
Bye.